So let's start a new topic, Faraday's law of electromagnetic induction. So Faraday's law of electromagnetic induction, we have this term EMI, electromagnetic induction. So what does this term mean?
Um,
Mm-hmm.
Sorry, once again.
Electromagnetic induction. Yes, Manya? EMI, electromagnetic induction, means that we change the magnetic field linked with the coil and we induce the current in that coil. See, in the previous section, we had talked about current carrying conductor, how the current carrying conductor produces magnetic field, right? So if we have a straight wire and this wire carries current I, then magnetic field around it is produced like this, right? So by, if there is any current in the conductor, then we can induce the magnetic field around it. A current carrying conductor produces magnetic field. This we had done in the previous section. Or moving charge produces, magnetic field around it. Or a current carrying conductor produces magnetic field around it. So how does current flow? Current is just nothing but rate of flow of charge. So whenever the charge moves, right, current is produced, and where there is current there is magnetic field. They are also directly related. This we had done in previous sections. So see, charge has its own electric field around it, right? So at any point r, if we write the formula for electric field intensity, then it is kq by r square. It has its own electric field around it, and when the charge starts moving, then this circle, the field, this is not a circle, it is actually spherical, because electric field intensity is 3D. It is in space, no? It depends on space coordinates. So when the charge moves, then the electric field linked with the charge will also move along with it. So basically, if we just focus at one point P and we just move the charge, then at this point P, the field intensity will change accordingly, no? And moving charge constitute current, right? Charge is moving, so current will be produced. And because the charge is moving, so there is change in electric field intensity, right? Because the charge is moving, so there is change in electric field intensity at any point P. And because of this movement of charge, current is produced, and because of the current, there is magnetic field. So we can say that if we change the electric field intensity, then if we change the electric field intensity, then it produces magnetic field. Okay? How is the electric field intensity changed? By moving the charge. Because charge is moving, so electric field is linked with the charges changing at any point, and because of the movement of charge there is current, and where there is current there is magnetic field. They are directly related. So change in electric field intensity produces magnetic field. This we have done in the previous section. Now in this sections we are talking about Faraday's law of EMI specifically electromagnetic induction. So here we change the magnetic field linked with a coil and current is produced. It produces electric field. So we are going to link like this way. So varying magnetic field produces electric field. As in this case, varying electric field had produced magnetic field. Now this time we are changing the magnetic field to produce the electric field. I hope this part is clear. And how do we change it? We'll learn about this thing in this section. Okay, please write this in your notebook. Next, we have the definition of electromagnetic induction. Electromagnetic induction. Please write the phenomena in which electric current, is generated by varying magnetic field. is called EMI. The phenomena in which, see, we are generating the electric current, we are producing the electric current by changing the magnetic field intensity at any point. And because here current is produced, so EMF is developed. So the EMF so developed is called induced EMF. EMF, full form of EMF is electromotive force. This we had discussed, I think, in the previous section as well. The EMF so developed is called induced EMF. And because of this, the current produces in the wire, in the coil, right? And that current is called induced current. Okay? We had done Ohm's law also.
Okay.
So V is proportional to I, or mathematically we write like this, or theoretically I proportional to V we write. And so V is equal to IR. This is Ohm's law, where R is the resistance of the conductor. Resistance, what is resistance? That which resists the flow of electric current. It is the obstruction or opposition to the flow of electric current. Right? So here also we can relate the EMF produced and the induced current like this. So EMF, we can denote EMF by small letter E and induced current by I into R. R is the resistance of the coil that we're taking. So we can write E is equal to IR, or if I want to find the induced current, so we write I is equal to E by R. So using Ohm's law, we can, relate induced current with induced EMF like this. Now, what is this EMF? This EMF is the electromotive force. Is it a force or what?
It's a force.
It's a force. I'll explain. This is not a force. Okay? ये force नहीं है.
Is it because of the charge would pull the no, it's not that.
Electromotive force. The word electro, wherever we find this word electric or electro, it is related to the charge. And motive means charge is in motion. And there is a kind of push that we are, pushing the charge to move it. Right? So let's consider a situation that we have a water tank placed at certain height. And if I want to, fill this water tank, isko full karna hai agar hame, then we need a motor, electric motor, so that water can flow easily in the upward direction, because water does not flow in the upward direction by itself. To move the water in the upward direction, we need a motor, electric motor, right? That, just creates a pressure difference, we can say, or pressure gradient, so that water can flow easily in the upward direction. But for the downward motion, do you need any motor for the downward motion?
No.
No motor is needed for the downward motion. We need it only in case of upward motion, because here the water is moving against the gravity. But here the water is just moving down by itself towards gravity, right? So in the downward motion, no motor is needed, while in the upward motion, we need an electric motor to move the water in the upward direction. In the same way, if we consider a charge, if the charge has to flow in a situation where there is potential difference, then if we have a conductor at higher potential and we have another conductor at lower potential, then charge can easily flow from higher potential to lower potential. And what if I want to move the charge from lower to higher potential? Then charge cannot move by itself. So for this, again, we need something like a motor that can push the charge to move from lower to higher. Okay? And that motor here is called EMF. So to move the charge from lower potential to higher potential, we need EMF. So EMF basically push the charges so that charges can move. Clear?
Yes.
And like voltage or potential difference, it is also measured in volts. Volt is the unit of EMF. And because we write E is equal to IR, so unit of EMF is volt, unit of current is ampere, and unit of resistance is ohm. So we can relate all these units. 1 volt is 1 ohm ampere. We can write like this, or we can define 1 volt like this using this relation. Please write this. What do you see in this, Jeff?
I think we discussed this yesterday.
Okay, fine. You explain then.
The force is downward, it's going downwards, and the magnetic field is going from north to south. And the conductor is placed in um it's perpendicular to the field.
We have a conductor connected with a cell, and because it is connected with a cell, so current will flow, can easily flow in the conductor, right? From positive terminal of the cell to the negative terminal like this. So this is the direction of current. Yeah, right? In the conductor from positive to negative. And because we have placed a current carrying coil, current carrying circuit, we have conductor, it is placed in a magnetic field. So this conductor will experience force, and the direction of force we can easily find by right hand palm rule. And why does this conductor experience force? Because it is a current carrying conductor, and where there is current, there is magnetic field. So it has its own magnetic field. So magnetic fields of both the conductor and the external magnetic field, they'll interact with each other. So because of the magnetic interactions, force will be experienced by the conductor, and accordingly we can find the direction using this rule. So this was the case where we have already a source of, a battery or a source of potential difference connected to the conductor. So current can easily flow through it. It's obvious, it's quite obvious because we have this cell here. It is connected with this. It is a source of current. So current, what can automatically flow in this? But what if we have a coil and there is no source of potential difference or a battery or a cell, anything that can produce current in the coil? So can we produce current in the coil when there is no, battery or a cell?
No.
No. So see, here comes electromagnetic induction. Because electromagnetic induction says that if you change the magnetic field intensity, varying magnetic field produces electric field or produces current, we can say. So current can be produced even without a battery in any coil. How can we produce the current in the coil? Just by changing the magnetic field intensity linked with the coil. So we had read about magnetic flux in the previous class. So what is magnetic flux?
It is the number of field lines crossing.
It is the number of field lines crossing an area is the magnetic flux. So if I change the magnetic flux linked with the coil, basically how will we change the magnetic flux? By changing the magnetic field intensity. Now you can see I put an arrow sign over this, but there is no arrow sign in the magnetic flux because it is a scalar quantity and magnetic field intensity is a vector quantity, right? So by changing the magnetic field intensity, if we change the strength of the magnets, or we change the orientation of the coil, or we move the coil up and down. So there are various ways, right, by which we can change the magnetic flux linked with the coil. Magnetic flux linked with the coil means the number of lines crossing the coil. So if we change these lines, so we're changing the magnetic field intensity, right? And on changing the magnetic field intensity, current can be produced in the coil. Even if there is no battery, it doesn't matter. We don't need a battery. We can simply move the coil up and down. We can change the orientation of the coil. We can change the strength of the external magnetic field. Our purpose is to change the magnetic flux linked with the coil. And once the magnetic flux linked with the coil changes, EMF is induced in the coil, and so the current is produced. So from here we conclude that if we change the magnetic flux with time, then we can induce current in the coil. And how do we get to know that there is current in the coil? So we can also connect an ammeter. And what does ammeter do? Ammeter is the device like this. As you can see here, only the letter is different. Here you are saying B, right? And there in ammeter we find A in ammeter. So what is the function of ammeter?
To measure the current.
It measures the current. And what if I attach a galvanometer to the circuit then? G. What does a galvanometer do?
Electrode potential. I mean, I don't know what that is.
See, it is a device used to detect feeble electric currents of microampere range. Microampere range. It is a device used to detect feeble electric currents, means electric currents of very small value of microampere range. So galvanometer basically detects the current, whether the current is flowing in the circuit or not, it tells us about that. And ammeter measures the exact value of the current. Voltmeter measures the EMF or voltage across the circuit, right? So we can connect a galvanometer with this circuit. And you can see here that in this circuit, we do not see any battery or any cell linked with the coil, right? Do we have a battery or a cell linked? Yeah, no. We just have a coil and the galvanometer, and we have this magnet. So Faraday's law of induction says that if we change the magnetic flux linked with the coil, if we change the magnetic flux linked with the coil, then EMF is produced. EMF is induced in the coil. And we can see a deflection in the galvanometer. Now you can see that if the circuit is stationary, if nothing is moving towards or away from each other, then everything is stationary, stable, right? Then the number of field lines entering the coil would be constant, no? There is no change in flux. How do we change the flux? How can we change the flux linked with the coil? Either we need to move the magnet towards or away from the coil, or we need to move the coil towards or away from the magnet. So by the relative motion of the coil and the magnet, we can change the magnetic flux linked with the coil, right?
Yes.
Okay. So जब तक ये stationary है, we have this coil here, and it is connected to the galvanometer, and we have placed a magnet near it. So unless or until we move the magnet either towards or away from the coil, there is no deflection in the galvanometer, no current will flow in the circuit. Current flows only when there is change in magnetic flux linked with the coil. Please write this. Now, what do you see in this, Jeff? Please explain.
When we bring the magnet towards the coil,
Mm-hmm.
the magnetic flux is getting increased, so the current would increase.
See, let's consider a situation where we have a coil and a magnet is placed near the coil. See, we do not need to connect this galvanometer. We connect the galvanometer for a sake only, because we need to find out whether the current is flowing in the circuit or not, right? So if this system, this setup is stationary, then no current flows, and we do not see any deflection, no deflection in the galvanometer, because the deflection in the galvanometer indicates the current flowing in the circuit. If there is no deflection in the galvanometer, means no current is flowing in the circuit. Why is no current flowing? Because there is no movement, right? There is no relative motion between the coil and the magnet. The number of field lines are still entering the coil, but this magnetic flux is constant. Phi B is constant, hence no EMF is induced. No current is produced. Because though it is placed in the magnetic field of the magnet, this coil is placed in the magnetic field, but the number of field lines entering the coil is fixed. And we can change the field lines entering the coil. How do we change it? We can change the strength of the magnet, right? So if we have a stronger magnet, then more field lines can cross through the coil, can pass through the coil. If we have a weaker magnet, then less field lines will pass through the coil. Or we can change the orientation of the coil. We can place the coil at certain angle in the magnetic field. Then magnetic flux linked with the coil will change accordingly because field lines will change. So there are various ways by which we can, change the magnetic flux linked with the coil. As we had discussed in the previous class, if we place the coil perpendicular to the magnetic field, then maximum number of field lines can cross through it. But if we place the same coil at a certain angle in the magnetic field, then fewer number of field lines can cross through the coil. And if you place the magnet horizontally or parallel to the magnetic field, then no field lines can cross through the coil. So by changing the orientation of the coil, by rotating the coil, by moving the coil up and down, by changing the strength of the coil. So there are various ways by which we can change the magnetic field lines crossing the coil, and hence the magnetic flux changes accordingly. So when there is change in magnetic flux, only then EMF is produced. Right? Now let's consider another situation. This is case 1. Now I'm taking case 2. In second case, I have the same magnet and the coil, but this time I'm moving this magnet towards the coil. See, EMF doesn't bother whether the magnetic flux linked with the coil is increasing or decreasing. EMF likes the change in the magnetic flux only. Right? So whether phi B is increasing or decreasing, EM doesn't bother that. It has nothing to do with that. So if we are moving the magnet towards the coil, now this time, because we are moving the magnet towards the coil, so what will happen? Field lines entering the coil will increase. As in this case, in the GIF you have seen, we were moving the magnet towards the coil and the number of field lines entering the coil were increasing. So the field lines will increase, and because of the increase in the field lines entering the coil, phi B increases. Flux linked with the coil will increase, right? And phi B increases. See, again I'm saying that EMF को उससे फर्क नहीं पड़ता कि whether the magnetic flux is increasing or decreasing. इसको फर्क पड़ता है, change हो रहा है ना, बस ठीक है, चलेगा. Because of the change in the magnetic flux, EMF is induced. And because there is EMF, so current is produced. And we can see this. How do we know that there is current in the circuit? We can see the deflection in the galvanometer in a certain direction. Suppose initially it was at the center, null point, right? Now it is slightly here. Initially the needle was like this at the vertical position. Now the needle bends towards the left or right side. So this, bending indicates the direction of current. Basically, it indicates the direction of current. If the galvanometer is going in this direction, means current in the wire is flowing in this direction. Right? And one more thing, if we move the magnet, see, there is one more situation that whether we are moving the magnet slowly or fast. So if we move the magnet faster, towards the coil, then del phi B by del T, no, this thing, the magnetic flux changes rapidly, no? So how fast this magnetic flux changing? It also tells us about the magnitude of the induced EMF. So if we are moving the magnet faster towards the coil, now EMF was, see, in this same situation when we had moved the magnet slowly, now we're moving the magnet faster. Again, the EMF is produced, but this time it has a greater value. Okay, so EMF will increase. You're moving the magnet rapidly towards the coil, EMF is increased and current so produced is increased. So we can see this time greater deflection in the galvanometer. Greater deflection in the galvanometer shows that now the amount of current, the current has a greater value. More current is there in the coil. Clear?
Yes.
Now let's consider another situation, the third situation. I'm going to clear this side. I hope you have written this part, no? Have you written?
Yes.
Now let's take third situation. In the third situation, again, we have the same magnet and the same coil. See this, these wrapping, this indicates the number of turns in the coil. That's why I draw like this for n number of turns. So we have this galvanometer linked with it. Now this time I'm moving the magnet away from the coil. So when you move the magnet away from the coil, then fewer lines will enter the coil now. Right? So magnetic flux is the number of field lines crossing the area. So magnetic flux linked with the coil is decreasing now. Because magnetic flux is decreasing. So again, because there is change in magnetic flux, right? So EMF is induced. Again, current is produced. And again, we see deflection in the galvanometer, but this time deflection is in the opposite direction. And current is flowing in the opposite direction like this. See, initially the deflection was, if it was, towards left, now the deflection is towards right, indicating the direction, that the direction of current is reversed, right? So if you are moving the magnet towards the coil, current flows in certain direction. And if you move the magnet away from the coil, current flows in the opposite direction. Again, if I move the magnet faster away from the coil this time, but we are moving it very fast. So del 5D, this changes rapidly, no? 5E will change rapidly. So if 5B is changing rapidly means more EMF is induced. We have greater value of EMF, more current, and more deflection in the same direction. Because see, because in this is the only case where we are moving the magnet away from the coil. For this particular case, first we are moving the magnet slowly, and then we are moving the magnet a little faster. So again, we'll see deflection, but greater deflection this time. So initially, if the deflection was this much, now we'll get a deflection, a bend, more bend in the needle towards this direction. So more current, indicating stronger current or strength of the current, that it is increased in the same direction. Please write this. Draw this circuit in your notebook. Yes. So this time we have two coils, and one is connected with a galvanometer and other is connected with a battery and a key. So because we have, this battery here, so if we switch on the circuit, if you close the key, then current starts flowing. Current will flow, no? When we switch on the circuit, and current starts flowing in the circuit because of this potential difference. So we know that current carrying conductor behaves like a magnet, or a current carrying conductor has, magnetic field around it. Now, because we have switched it on and current is flowing in the circuit, in the coil, so there is magnetic field around it. And this field lines will go to the neighboring coil as well. and it is placed very close to it, not very far. So the field lines will go to the neighboring coil, right? Like this. So there is a, fixed magnetic flux linked with the coil 1 as well. Now, because this is a source of DC, we have no AC supply here. We have connected it to battery. So a constant value of current is flowing in the circuit, let's say 10 ampere. Because we have a constant current flowing in the circuit, so hence constant magnetic field is produced around it. And because current is constant, magnetic field is constant, and so is the magnetic flux. So there is no change in magnetic flux at all. So number of field lines entering the coil 1 is also fixed. So no deflection can be seen in the galvanometer because there is no change in flux at all. So no deflection we can see in the galvanometer. Now what if I switch it off? I open the key, then current will decrease rapidly to 0. So there is a change in current, right? And because of this change, there is change in magnetic field as well, because current and magnetic field intensity, they are directly related. And because of the change in magnetic field intensity, there is change in flux. Flux will decrease. So number of field lines entering the coil 1 will also decrease. Flux linked with coil 1 will also decrease. And we can see the deflection in the galvanometer. Okay, again, I'm going to turn it on. Okay. So when we switch on the circuit, again the current will flow in the circuit, right? So current will increase rapidly from 0 to 10 amperes. So when this change occurs from 0 to 10, then again, see, magnetic field is increasing, magnetic flux linked with the coil 2 is increasing. So magnetic flux or number of field lines entering the coil 1 will also increase. Again, we'll see the reflection in the galvanometer, but this time in a positive direction. Okay. So whenever we switch on or off the circuit, for a very small moment, we will see deflection in the galvanometer. If we see the deflection in one direction at one point, then we'll see the reflection in other direction when we switch it on or off, right? Clear? Please explain this to me.
So when we switch on the switch, the current will flow and the magnetic field will be produced and it will go in coil 1, and the current would, no, not the current, it would go in the other coil, and there will be a constant magnetic field which will
So only
cause
when we switch it on or switch it off, then current increases rapidly to 10 and decreases rapidly to 10, right? Rapidly to 0. Only then we see deflection for a very small moment in the galvanometer. So it goes to one side and goes back to the null point for a very small moment. Because current becomes steady after some time. No? We switch it on, current increases from 0 to 10 and it becomes steady at 10. So when it becomes steady, it becomes constant, then we see no deflection in the galvanometer. It goes back to the null point. Null point is the 0 point, no deflection point.
okay.
Okay, so, and one more thing. Here we have discussed that when we switch it on, if the deflection is in one direction, on switching it off, we see the deflection in the opposite direction. Means we see the change in the direction of current by switching it on or off. The same thing we had discussed in the previous section where we have moved the magnets. So when we move the magnet towards the coil, we see deflection in one direction. And on moving the magnet away from the coil, we see deflection in the opposite direction. So there is a change in current when we change the field lines, right? See, how is the current produced? In which direction the current is produced? Now this we need to know. So for this we have a law, Lenz law. Write the heading. Lenz law. According to this law, the direction of induced EMF is such that it always opposes the cause producing it. The direction of induced EMF is such that it always opposes the cause responsible for its production. So to understand this, let's consider a situation where we have a coil and a magnet. We have this coil and the magnet. So this is the north pole of the magnet and this is south. So if we move the magnet towards the coil, because we are moving the magnet towards the coil, so the number of field lines and entering the coil will increase, right? Because number of field lines entering the coil is increasing, hence the magnetic flux linked with the coil is also increasing. And because of the change in magnetic flux, EMF is induced, so is the current. Current is produced. Now, what is the direction of current? See, direction of induced EMF or direction of current is such that it always opposes the cause producing it. So what is the cause? Cause is the movement of the magnet, right? Because of this movement, only we can see the current in the coil. And the result is the EMF induced or current produced in the coil, right? So it is going to oppose. So current will flow in certain direction that will oppose the movement of this magnet towards the coil. So how will the current flow? Because the magnet is moving towards the coil. So current flowing in this is going to oppose this change, right? Current will start flowing in the anti-clockwise direction. And we know clock phase rule. If the current is flowing in the anti-clockwise direction, then this phase is the south, becomes the north pole, and the another phase becomes the south pole. So now the biggest magnet is moving towards the coil. So we are getting this north pole here. So it is going to repel it. So it is opposing the cause. Because of which, see, because of this movement, current is induced in this coil, right? And it is opposing that only. It is producing the current in this way that we are getting the north pole, the same pole here, so that this magnet doesn't move any further towards the coil. It will not move, no, towards the coil because it is going to repel it. Now let's consider another situation. Again, but this time I'm going to move the magnet away from the coil. So the number of field lines entering the coil will decrease, right? Again, the current will be induced, but this time current will be induced like this in the clockwise direction to oppose the change. The current will produce like this in the clockwise direction. So we get the south pole here and the north pole here. Again, it is opposing the change and it is going to attract it towards it. So when it was moving towards it, it was repelling it. Now it is moving away from it, so it is attracting it. So you can see it is opposing the cause producing it, and therefore we put a negative sign with, because EMF induced is, directly proportional to the magnetic flux change, rate of change of magnetic flux. If we are changing the magnetic flux faster, then we see more EMF in the circuit or more current in the circuit. And we put a negative sign here because of this reason, because EMF produced is opposing the cause producing it, and therefore we put a negative sign. Yes, Manya. Please write the heading. Faraday's law of electromagnetic induction. See, this law states that the magnitude of the, please write this, the magnitude of the induced EMF in a circuit, you there, is equal to the time rate of change of magnetic flux through the circuit. As we have discussed, that if we change the magnetic flux, at a faster rate, then more EMF is induced. So magnetic induced EMF depends on the change, how the magnetic flux is changing, how fast or how slow the magnetic flux is changing. So if the magnetic flux is changing at a faster rate, then more EMF will be induced. And if the magnetic flux is changing at slower rate, then less EMF is induced. So if you're moving the magnet towards the coil faster, then you can see the more deflection in the galvanometer. If you're moving the magnet slower, you'll see less deflection in the galvanometer. And according to Lenz law, we know that the EMF induced opposes the cause producing it. It opposes the change, right, in magnetic flux. And therefore, we put a negative sign. Therefore, we put a negative sign. Why do we take a negative sign? Why this negative sign is taken?
Because it opposes the direction.
It opposes the change in magnetic flux. It opposes the change in magnetic flux. And to remove the sign of proportionality, we add a constant. And here the constant is 1. So we can directly write E is equal to minus del phi B by dt. So this is for 1 turn. If the coil has just 1 turn, then we write like this. For the coil with n number of turns. So if the coil has n number of turns, then we just multiply it by n. It becomes n times. Clear? This is for n turns and this is for 1 turn. Clear?
Yes.
Okay. Yes, please look at the screen. Can you see this? Is it visible?
Yes.
So in the previous section, we had one question there. We had discussed phi versus T graph, magnetic flux versus time graph. So from magnetic flux versus time graph, we can also draw induced EMF versus time graph, right? So this is the formula of induced EMF minus n del phi by dt. So EMF graph should be negative when the magnetic flux graph has a positive gradient. Means magnetic flux graph has a positive gradient. Gradient because magnetic flux is changing here, right? So that's why we use the term gradient here. You might have seen this term with voltage gradient or any other gradient. Gradient means how the quantity is changing with respect to time or with respect to distance. As we had done in the previous section, that E is V by D. So electric field intensity is voltage gradient, potential gradient. Because electric field intensity is varying with this potential gradient, because potential with respect to distance tha yahan pe between the plates, no? So gradient का मतलब होता है कि कैसे एक क्वांटिटी जो है वो दूसरी क्वांटिटी के रिस्पेक्ट में चेंज हो रही है. So EMF graph should be negative when the magnetic flux graph has a positive gradient. Means if del phi by B by del T, positive gradient means if del phi B by del T is positive. then EMF is negative. Because we have a negative sign here, right? And what if we have magnetic flux? What if magnetic flux has a negative gradient? What if magnetic flux is decreasing with time then? We have this becomes negative and we have one more negative here in the formula. So minus minus becomes plus, no? Negative and negative gives you positive. Then your EMF is positive. Clear?
Yes.
See, if your magnetic flux is increasing uniformly with time, means we can consider a situation where we have a coil and a magnet and we are moving the magnet towards the coil with constant speed or constant velocity. Then change in magnetic flux with respect to time, the magnetic flux will change uniformly with time. Equal change in magnetic flux in equal time. So if I want to draw the graph where I want to draw equal change in magnetic flux with equal time, and it is increasing because we are moving the magnet towards the coil, then how will we draw it? We can draw like this. This is your phi b versus time graph. So this is phi b versus time graph. So if the magnetic flux is increasing at a uniform rate, at a constant rate with time, no? Then we draw a straight line graph. So this indicates that magnetic flux is changing with time, but it is changing uniformly. It is changing at constant rate. And because here you can see del phi E by del T is positive, so EMF is negative. And because we are getting a constant value of del phi V by del T in this case, so we'll get a constant EMF. अगर आप magnet को coil की तरफ move कर रहे हो and you are moving the magnet towards the coil at constant speed, then you will find that there is equal change in magnetic flux in equal time. So every time you will get the same value of induced EMF. There will be no change in the EMF induced. Only EMF, the value of EMF changes only if you move the magnet a little faster or a little slower. If you change the speed of the magnet towards or away from the coil, only then the value of EMF will change. But if you are moving the magnet at a constant pace, then we have a constant EMF induced in the coil. Okay, so we have a constant value of negative EMF, right? So we are going to draw a parallel line for EMF like this. For EMF, we have yellow. I'm using this yellow color for EMF. So we are going to plot. We are plotting the same, for graph on same graph for both E versus T and phi B versus T. So what if this phi B is decreasing? What if we move the magnet away from the coil? Then magnetic flux linked with the coil will change. But because it is decreasing this time now, so we have a negative slope. Why are we getting negative slope here? If we move the magnet away from the coil, then the number of field lines entering the coil will decrease. Because the number of field lines entering the coil is decreasing, so del phi B by del T, the rate of change of magnetic flux is negative, and we'll get a positive value of EMF. Right? So positive constant value of EMF because it is decreasing at a constant rate. See, you can see it is uniformly decreasing, no? So it is decreasing at a constant rate. So we'll get a positive value of EMF. This is the EMF that we'll get. नहीं आया.
Can you tell me about the constant EMF?
देखो, अगर आपका phi भी चेंज तो हो रहा है, ये तो पता ही है हमें, है ना? सपोज 0 सेकंड पे आपका जो phi b है वो 1 वेबर है, एंड आफ्टर 1 सेकंड इट बिकम्स 2 वेबर, आफ्टर 3 seconds 2 seconds it becomes 3 weber, after 3 seconds it becomes 4 weber. So every time magnetic flux is changing at constant rate, it is increasing by 1 in 1 second. right? So del phi b by del t has a constant value. The change in magnetic flux with time, it has a constant value.
Okay.
Because every time magnetic flux is changing at a constant rate. After every 1 second, we can see the change in magnetic flux is 1 Weber after every 1 second. So del phi b by del t has a constant value. And because this is constant, and this is the formula minus n del phi by b by del t. And if you are keeping this as constant, so you will get a constant value of EMF. And therefore we draw a straight line, because when we draw a straight line means we have a constant value of EMF. But our phi b is not straight like this. It is not parallel to time axis. It is inclined to time axis. Why? Because phi b is increasing with time. So when our phi b, the magnetic flux, is increasing with time uniformly at a constant rate, then we get a constant value of EMF. Okay? But with a negative sign. Why? Because we have a negative sign in the formula. Because we have a negative sign in the formula. So इसलिए we are just drawing the straight line below this line, no, negative, along the negative direction. We have drawn it. In the second case, let's take another situation where your phi b is decreasing with time this time, because you are moving the magnet away from the coil. So if you move the magnet away from the coil, then suppose initially we have 10 Weber linked with the coil. Magnetic flux linked with the coil was 10 Weber initially at 0 second. So now you are moving it away from the coil. So after 1 second, let's say it becomes 8. After 2 seconds, it is now 6. After 3 seconds, we see that it is now 4. And why is it decreasing? Because now this time we are moving the magnet away from the coil. So magnetic flux, lines of force will decrease, and accordingly magnetic flux will change. So you can see again we have a constant change. No? कितना वेबर पर सेकंड चेंज आ रहा है? 2 Weber per second. After every 1 second, 2 Weber is decreased. No, it is decreased by 2 Weber. So change is 2 Weber per second. So we have a constant value of del phi b by del t again, but it is a negative constant, negative value, right? So magnetic flux graph has a negative gradient. It is decreasing, but constantly in a every time after every 1 second, it is decreasing by 2 Weber. So we'll get a straight line again, inclined to time axis, but this time we have a negative slope because it is going down. It is decreasing, right? And because it is decreasing, so del phi b by del t has a negative value. And because it is negative, therefore, your induced EMF is positive. And positive constant. Because del phi, see, phi b is decreasing with time, but this ratio is a constant. आपका जो phi b है वो टाइम के साथ डिक्रीज हो रहा है ना, 10 से 8 से 6 से 4. बट जो del phi b by del t है वो तो कांस्टेंट ही रहेगा ना. Because every time if you take this interval, 8 minus 10 आएगा upon 1 minus 0. You'll get 2 Weber per second. Every time it is decreasing by 2 Weber per second. यहाँ पे भी 2 Weber per second. यहाँ पे भी 2 Weber per second. No? तो del phi b by del t तो constant ही है. Phi b कम हो रहा है, but del phi b by del t is a constant 2 Weber per second. And therefore EMF is a constant. But this is positive constant this time because we are getting a negative del phi b by del t. So minus minus becomes plus, and we get a line inclined to time, parallel to time axis on the positive side. So for if you have, d phi by dt like this, अगर आपके पास ऐसा है पॉजिटिव ग्रेडियंट है, then you'll draw EMF like this. ठीक है. और अगर आपका del phi b by del t ऐसे जा रहा है, ऐसे जा रहा है, तो EMF आपका ऐसे जाएगा. I hope this part is clear.
Yes.
And what if there is no change in magnetic flux? What if we are keeping the magnet and the coil at the same place where they are? Then
Then the gradient would be 0. So a
the
straight
gradient will
line
be
on
0,
X.
and no EMF will be induced. And we can draw line here on the time axis only for EMF. We will do this. We have a question based on this. See, now please let's read this content first and then we'll move to the questions. Two ways we can change the magnetic flux and therefore induce an EMF in a loop. So with this we have discussed in the previous section as well. So we can change the magnetic flux by changing the strength of the magnetic field. More magnetic field indicating more lines entering the loop and stronger magnetic flux, right? Move the loop into or out of the magnetic field. We can move the loop up and down in the magnetic field, and so the number of field lines entering the loop will change. And we can change the shape of the loop while it is inside the field. If we change the shape of the loop, then number of field lines entering the loop will change, and hence the magnetic flux linked with the coil will also change. And if we rotate the loop inside the magnetic field, again we can change the area. We are changing the area of the loop perpendicular to the magnetic field. Again, the magnetic field lines entering the coil will change, right? By changing the orientation of the coil in the magnetic field, lesser lines, cross the loop. And how do we increase the amount of EMF induced? So we can increase the EMF induced in the loop by increasing the area of the loop. आपको जो EMF induced है वो कैसे increase करेंगे loop में? We can increase the area of the loop. We can increase the magnetic field strength of the loop in which the loop is placed. Or we can increase the rate at which the magnetic flux changes by moving the loop faster or changing the magnetic field strength more quickly. Because if we move the loop faster towards or away from the coil, we are changing the magnetic flux at a faster rate and more EMF will be induced. Or we can change the magnetic field strength quickly so that the field lines will change accordingly and more EMF will be induced in the coil. I hope this part is clear. You can ask the doubts.
Yes, it's clear.
Next, we have this question now. So we have a square loop. It has 5 turns and it is moved through a uniform magnetic field. Using the included magnetic flux graph, draw a corresponding EMF graph. So from this, we are going to draw EMF graph. So certain things are given to us, like, you can see the time interval, you can see the flux, and you can, the number of turns in the square loop. See, in the first case, from 0 to 0.2 second, we have an increasing slope, right? So magnetic flux, you can see it is changing with time. At t is equal to 0, flux was 0 Weber, no? And after 0.2 second, flux has become now 4 Weber. So what is from 0 to 0.2 second, your change in magnetic flux is final magnetic flux is 4 and initial magnetic flux is 0. So we can write 4 minus 0 divided by rate of change of magnetic flux we are finding here. And the time interval is 0.2 minus 0. What will you get? Del phi b by del t value is 4 upon 2 into 10. No, this is 20. And because we have to find the induced EMF, the value of induced EMF, it has a constant value here because you can see flux is increasing at a constant rate. So induced EMF is minus n del phi b by del t. So negative sign, number of 5, we have 5 turns here into del phi b by del t is 20. So the induced EMF is minus 100 volt. So you can see when your del phi b by del t is positive, so we're getting a negative value of induced EMF. So it has a constant value, negative constant value in the first case, right? So if I want to draw it, how I'm going to draw it? Negative 100 कैसे draw करोगे? We can draw like
The gradient would be negative.
gradient is positive. The magnetic flux gradient, that's del phi by b by del t is positive. EMF is negative. So we'll draw a
Oh
line
yeah, the
parallel.
EMF would be negative.
Yes. For the first case when we're going from 0 to 0.2 seconds. Now from 0.2 to 0.4 second. Yes, Manya. From 0.2 to 0.4 second. Do you see any change in the magnetic flux here in this time period?
No, it's constant.
So phi b is constant. So if the magnetic flux is constant, then will there be any change in, induced EMF or any current in the circuit? Because magnetic flux is constant, so del phi b by del t is rate of change of magnetic flux is 0. Here in this time period, magnetic flux is constant. It is 4 Weber only, right? From 0.2 to 0.4 seconds, magnetic flux is constant. So there is no change in magnetic flux, and hence no EMF will be induced in the circuit. No current will be seen in the circuit. So if you're drawing EMF time graph, E versus T graph, then how will you plot it on E versus T if magnetic flux is constant? On E versus T
Um,
graph, we can plot like this, Hanji.
so it would be a straight line LT.
It would be a straight line from 0.2 to 0.4 seconds, like this, on time axis. On time axis. Why on time axis? Because on time axis, E is 0. Abscissa आपका है ये. Time is your x-axis, right? Abscissa values. No? So we have no ordinates here on x-axis. No ordinates means no EMF. No y coordinate, right? So for if we have magnetic flux like this, we'll draw for induced EMF like this on the time axis. And now for the next interval from 0.4 to 0.6 second, the time interval is 0.4 minus 0.6 minus 0.4. The third interval, this interval, 0.2 second, right? And the change in magnetic flux is, what is the final magnetic flux in this case?
0,
And initial?
4.
Final magnetic flux is 0 and initial is 4. So we'll write final magnetic flux minus initial magnetic flux. So it is minus 4 Weber. And what is E? E is minus N del phi B by del T. So we can see that we have a negative slope here. No, it is going down. So del phi B by del T is negative. So now we will get a positive value of EMF. Right? So again, find the value. You'll get the same value because the change is the same. So minus 5 into del phi B is minus 4 and divided by 0.2. So you'll get 100 volts this time, plus 100. So how will you draw the graph for EMF for this particular situation?
At positive
Straight
100
line, yes,
volts.
straight line like this, है ना? This is what we'll get. Now you know how to draw it. See, we can also join the lines. Just say,
Yes.
though we are getting this value first for the first time period, for the second time period, we're getting this value. For the third time period, we're getting this value. So it's like stairs, no? We're going up and up and up. So we can join these lines. Either we can use dotted lines or we can just use solid lines as you can see here in this case. Okay? So we can join like this. Clear? Any doubt?
No, it's clear.
We have two questions here. An EMF will not be included in a loop when See, if you are decreasing the magnetic flux, there is EMF, right? EMF will be induced in the circuit if you are changing the magnetic flux basically. If you are changing the magnetic field strength, because of the change in magnetic field strength, again, flux will change and hence EMF will be induced. No? And if you are changing the area of the loop perpendicular to the magnetic field changes, again, EMF will be induced because field lines will change. What if the loop is placed or moved horizontally with its area always entirely within the uniform magnetic field? What is it? Have you understood? This is the case where we have this external magnetic field and we have a coil. And we are moving the coil horizontally. Means I'm moving the coil like this, parallel to its original position. Or we can say we are moving the magnet like this. Then in that case, you can see the field lines remains constant. There is no change in the field lines. And because there is no change in the field lines, hence no magnetic flux change, right? No EMF will be induced. So EMF will not be included in a loop when a loop is moved horizontally with its area always entirely within the magnetic field. So area, everything is there in the, even if you have placed the coil like this and you're moving it. So the coil is totally in the magnetic field. So there is no change in the magnetic flux linked with the coil, hence no EMF will be induced. So D part is the correct option. ठीक है?
Yes.